So far we have been analyzing the performance and characteristics of a DC shunt motor. In a shunt motor, the armature is connected across a DC voltage supply and the field excitation coil is connected across the armature terminal. This is the configuration of a shunt machine. Today we will discuss about the characteristics of a DC series motor. As we know, as the name suggests, in a series motor the field winding is connected in series with the armature. So, while in a shunt motor the field flux remain essentially constant with variation in load torque or armature current, in a series motor is strongly influenced by the load torque. This brings about a marked change in the torque speed characteristics and all other characteristics like speed current characteristics of DC series motor, which we will discuss today. Whether the excitation is obtained from a shunt field or from a series field, the basic equation of a DC machine holds, that is, the induced voltage E across the brushes is given by back EMF constant into phi, the field flux into armature current. Similarly, the generated torque T E, the same K into same field into I A, and of course, the terminal equation V T equal to E plus I A into R A total. Now, while for shunt machine phi f is a function of I f which can be controlled independently, this is shunt machine. For a series machine phi f equal to a function of I A, which is given by the magnetization characteristics of the machine. This is series machine. Also, RA for shunt machine, at least during running condition, normally is RA total is normally equal to the simply the armature resistance, possibly including the brush drop. For a series machine, RA total even during running condition is equal to armature resistance plus the series field winding resistance. So, let us see how the torque speed characteristics and all other characteristics gets modified because of the dependence of the field flux on armature current. Initially, we will assume that the magnetic circuit of a shunt of the machine is linear, that is, this f is a linear function and phi f can be given by some flux constant k f into I A. In this case, the induced EMF E becomes k f this is omega I A, and torque becomes k kf ia square. So, Vt equal to E plus Ia Ra plus Rac, this is equal to k kf omega plus Ra plus Rac into Ia, or Ia equal to Vt divided by k kf omega plus Ra plus Rac. Or omega plus Ra plus Rac by kkf equal to into Ia equal to Vt by kkf. So, this is the speed versus current characteristics. We see this is like a rectangular hyperbola, whereas the torque current characteristics is Te equal to k kf Ia square, which is a equation of a parabola. From these two we can easily derive the torque speed characteristics of the series motor, that is Te equal to k kf Ia square equal to k kf Vt square divided by or Te into omega plus Ra plus Rac divided by whole square equal to Vt square by k kf equal to Vt divided by square root k kf whole square. So, the torque speed characteristics is given by This is the torque speed characteristics. The current speed characteristics is and torque current characteristics is let us now draw them. Easiest one is to draw the torque current characteristics. Proportional to Ia square. The speed current characteristics, and the torque speed characteristics. This characteristics asymptotically approaches this line is omega equal to minus plus RAC by KF. Again this is somewhat similar, but this line is again omega equal to minus RA plus RAC by KF. For a comparison, let us also draw the corresponding characteristics for shunt motor. For a shunt motor, torque is proportional to Ia. So, up to some point, this is shunt motor. Up to this point, shunt motor generates, up to this current, shunt motor generates more torque than the series motor, but beyond that, series motor can generate a much larger torque. For the shunt motor, this characteristics is a straight line. Also, for a shunt motor, the torque speed characteristics is a straight line. There are several features to note in these idealized characteristics of the DC series motor. If we look at the speed current or speed torque characteristics, we find that the characteristics are asymptotic to IA equal to 0 or TE equal to 0 line. That means, as the load on the motor is reduced, the speed tends to increase dangerously, and there is as such no finite no load speed of this series motor. Therefore, a series motor should never be run on no load, then the speed can rise to very high value, which can be dangerous. For the same reason, it is not possible to operate this motor in a regenerative braking region, because we know for regenerative braking operation the motor must be driven beyond its no load speed, so that the current reverses. So, this is not possible for a series motor. The characteristics we have drawn so far are somewhat idealized, in the sense we have assumed that the flux phi f to be proportional to IA. While this is true for small values of IA, for larger values of IA, the two effects, the saturation of the field and the armature reaction effect, tends to violate this condition. So, normally phi f will be a nonlinear function of IA and will tend to saturate for larger values of IA. If we take saturation into account, then these characteristics gets modified to some extent. For example, this torque current characteristics more or less approaches the shunt characteristics for large values of current. Similarly, the drop in speed is not as much if we consider the saturation. Drop in torque is also smaller. This is considering saturation. So, when saturation is taken into account, the characteristics of this motor changes in this manner. So, how do we really calculate the characteristic parameters of a series motor taking into account the saturation? For that, we will have to first obtain the OCC of the machine. For this, the machine will be run as a generator using a prime mover at some constant speed. and its terminal voltage will be measured. The series field coil will be excited from a separate source of appropriate rating. And the data generated can be plotted as shown. At omega equal to omega 1. We know that the induced voltage is proportional to the rotational speed, therefore, OCC at any other speed can be obtained by simply scaling one OCC by the ratio of the speed. The other equation, the load, so called load line, is given by Vt equal to E plus Ia into Ra plus RAC, which is again a straight line. At the operating point, both the OCC and the load line equation must be satisfied. So, this will be the operating point. This will be the Ia and this is E. So, at a given terminal voltage, if the machine runs at a speed omega 1, then we can find out the corresponding armature current and the induced voltage in this manner. Then the mechanical power equal to EIA and the torque developed is thus we will be able to find out the torque at the speed omega 1. Similarly, the OCC can be scaled at different speeds, and for the same applied voltage we will be able to find out E and Ia, and we will be able to generate the torque speed characteristics. So, let us solve one or two problems to explain these methods. Let us say we have a DC series machine. Four pole and flux per pole equal to 4.5 milliweber per ampere. We are assuming that phi f is proportional to Ia, that is linear magnetization characteristics. The load torque TL is proportional to omega and omega square, and TL equal to 30 Newton meter when n equal to 1000 RPM. The armature is wave bound. has Z conductors, number of conductors Z equal to 492. So, we have to determine the speed n and current I a when this motor is connected to 220 volt. Total resistance R A plus R A C equal to 2 ohm. Now, the back EMF as a function of current can be found as follows. Number of poles by number of parallel paths. From the given data, IF is 4.5 into 10 to the power minus 3 into Z is 492 by 60, P equal to 4 and wave bound, therefore, A equal to 2 into armature current into RPM. So, EA equal to 0.0738 in IA. This assumes linear magnetization current. And what about torque? Torque we know EA IA by omega equal to EA IA by 2 pi to n by 60. So, this comes to 1 by 2 pi E is phi n Z by 60 to P by A into 60 IA by n. This comes to phi IA Z by 2 pi into P by A. So, TE comes to 1 by 2 pi into 4.5 into 10 to the power minus 3 into IA. This is the flux into IA into 492 to number of poles is 4, number of parallel path is 2. So, this comes to 0.705 IA square. Also, we know E equal to V minus IA into RA plus RAC. From the given data, this comes to 220 minus 2 IA. Therefore, 8 in IA equal to 220 minus 2 IA, or 2 plus 0.0738 in IA equal to 220. This is the current speed characteristics of this machine. Then torque is (0.705) IA square, substituting from the previous equation. Also the load torque equal to sum K L into n square, where we have given 30 Newton meter equal to K L into 1000 square. Therefore, K L equal to 30 divided by 1000 square, which comes to 3 into 10 to the power minus 5 Newton meter per RPM square. Under steady state, TL equal to TE. Therefore, into 10 to the power minus 5 n square equal to 0.705 into 220 divided by 2 plus 0.0738 n whole square. Solving this, we get n equal to 662.6 RPM, and the corresponding IA comes to 4.32 amperes. This is one problem where we have seen how to find out the speed and current of a DC series machine when we assume that the magnetic circuit is linear. However, in most cases, in most practical cases, the magnetic circuit will not be linear. Therefore, let us try to solve a problem where the magnetic circuit of the series motor is not linear. So, for that, let us assume a DC series motor with the following data. This has RA plus RAC equal to 0.08 ohm. Now, the OCC is determined at 1200 RPM. OCC at 1200 RPM is given by the following data. IA Vt at 40 amperes, Vt is 62 volts. At 80 ampere is 130 volts. At 120 ampere it is 180 volts. At 160 ampere this is 222 volt. At 200 amperes it is 250 volts. At 240 amperes it is 270 volts. At 280 amperes it is 280 volts. To 92 volts. Suppose this is connected to a voltage source of 250 volts. How do I find out the torque speed characteristics of this machine from the given data? For that, let us first ask the question, let us say for some values of armature current IA of let us say equal to 75 amperes. What will be the induced voltage? Then E will be equal to we know at 75 amperes IA equal to 75 amperes and omega equal to n equal to 1200 RPM. We can find out the value from let us say from the linear interpolation of this table. E at 1200 will be equal to E at 80 is 130 minus this comes to 121.5 volts. So, in order to have a speed of 246, the N must be 246 by 121.5 into 1200. So, this comes to 2430 RPM. So, when connected to a 250 volt source and drawing a current of 75 ampere, the machine will run at 2430 RPM. What will be the torque? T omega equal to E I A so torque will be equal to 60 by 2 pi into 2430 into 246 into 75, this gives to 72.5 Newton meter. Therefore, in this manner we can calculate the for different values of armature current we can find out the torque and speed. So, IA we have done it for 75 amperes, E came out to be 246, E at 1200 from the given magnetization characteristics is 121.5, N in RPM comes to 2430 and T in Newton meter comes to 72.5. Similarly, we can do the similar calculation for 100. Here it comes to 242, 155, 1874 and 123. 200, 300, 400 amperes, from this data we will be able to draw, let us say, torque speed characteristics, torque current characteristics when connected to a 250 volt supply. Speed current characteristics, and the torque speed characteristics. We observe that in a DC series machine, as the armature current increases, the torque increases almost proportional to the square of the armature current, which means at large current, at low speed and large current, the series machine can generate considerably larger torque compared to a shunt machine. Therefore, these were preferred for machines where large starting torque is required. For example, for traction motors, DC series machine has been traditionally used. However, it has to be remembered that a DC series machine does not have an intrinsic no load speed. In fact, if the load on the DC series machine goes on reducing, the speed can increase dangerously. For example, we have seen here at 400 rpm, whereas the speed is 900, at 400 ampere, whereas the speed was 900 rpm, at 75 ampere the speed has become almost close to 2500 rpm, which is an increase by a factor of more than 2.5. In a shunt machine this is not so, therefore, the speed remains almost constant. So, a DC series machine must be always be run with a load in order to avoid dangerous high speed. A few other salient features about the ideal characteristics of a DC series machine. We see that in a DC series machine, the torque speed characteristics is proportional to the terminal voltage square. In other words, it is not possible, unlike a shunt motor, in a series motor reversing the armature voltage polarity does not allow the motor to run in the reverse direction, because since torque is proportional to Ia square, whether current flows in this direction or in this direction, it produces motoring torque only. Therefore, speed cannot be reversed simply by interchanging the armature terminal. In these cases, therefore, in most cases for DC series machine, if one wants to generate negative torque, then normally it is necessary to reverse the field winding also, that is in order to generate reverse torque, one would need to reverse the connection of the series field, that is even with this, it is not possible to obtain regenerative braking characteristics of the DC series machine as such. The reason is very simple and can be understood as follows. For example, suppose we have a DC series machine whose OCC is given by this curve. When operated as a motor, Vt equal to plus Ia Ra or E equal to Vt minus Ia. Therefore, the load line is somewhere here. And this is the point where the machine operates. Now, suppose I had interchanged the polarity of the field terminal. In that case, for negative current, similar characteristics will be obtained. However, there will be normally no intersection point between this load line and the reverse magnetization characteristics because of saturation. Therefore, even with reverse field winding, it will fail to operate in a regenerative braking mode. The only way regenerative braking mode is possible is if by some means the load line can be during braking operation can be reduced. As we have seen, we will see again that this can be achieved by using a electronic power supply called the chopper. Hence, normally a DC series machine will not allow regenerative braking, but using chopper you can go for regenerative braking of even DC series motor. This and other starting and braking techniques for and speed control techniques or DC series machine we will discuss in next few classes. Thank you.